recording. So today's topic is Gaussian mixture model. In the last class we studied k-means clustering. So the basic idea is we have data which is distributed. In the previous class we saw different distributions which were unimodal, which means okay, we have one cluster of data and then we were trying to find different approximations or different standard models to approximate that distribution. Means the samples are given to us, we want to estimate a model and which we'll be further using for asking more questions. Okay, but if the samples are all lumped together, then we saw different distributions, like we saw Gaussian distribution, we saw exponential distribution, like that there are so many distributions which are available, standard distributions. But then what do we do if the data is not unimodal? It is not just one cluster, but it is small heaps of samples distributed in the space. So in that case, it is useful to study what is there in those heaps. So why is the data not uniformly spread, or why is it not everywhere? Why is it just concentrated in certain pockets? So that is called unsupervised clustering analysis, or it's also called unsupervised learning, because nobody is telling you these are the labels of different classes, just that the classes are lumped together and you are trying to see the structure, the lumps in them, and trying to find, okay, they are different classes. And then you can manually study later what is there in this lump, what is there in this lump. So that is the idea of clustering. So we saw a very basic technique of clustering called k-means clustering. It is very intuitive algorithm which just, this is the loss function which is called the distortion measure. It will, okay, let us say we have got two clusters. So each cluster will have a mean and a variance, or let's say here in this case only a mean is there. You can also have a variance term, divide by sigma square. But in this case it is just a mean term. Mu k is the mean, and then Rnk is the membership function, which means the sample n belongs to the kth cluster. So it is a hard assignment, which means sample n can belong to only one of these clusters. It cannot belong to both the clusters together with some soft weight. It is just either 1 or 0, right? So Rnk will be for each n. Rk will be either 0 or 1, means in this case 1 or 2, and which means Rk will be 1 for 1 or 1 for 2. Okay. So based on which cluster it belongs to, we are trying to minimize the spread of the data within each cluster, right? So this is the meaning of this distortion measure. K is the cluster index, n is the sample index, and that is it. So basic idea is that this L avoids very large clusters plus a few singular ones. Means if I cluster this whole data in one heap or one cluster, and just this one point I put it separate, I say this is a separate cluster, that is not a very good thing which I want to get. Rather, so that is why I designed my distortion measure in this way, which will penalize. It will say do not do this, because in that case my x minus mu k for this cluster will become very large. Although for this cluster it will be very small, but for this cluster it will be very large. So on an average, when you sum over all of them, the whole thing will be very large, right? So that's the idea of k-means clustering. Now, this is the model, how do you find the optimal values of parameters, what are the parameters? The parameters are the cluster centers, the mu's, and the cluster assignment function, the Rnk, right? Which sample belongs to which cluster, right? These are the two parameters. Now, if you look at this loss function, so we cannot optimize both together, so we'll do step by step. So we use an iterative algorithm where we first optimize one parameter, then keeping this fixed, optimize the other parameter, keeping that fixed, optimize the first parameter, then again second. In this way we iteratively update our parameters, right? So let us say I fix my mu's, I just put them somewhere. I have to now optimize my Rnk, which means the cluster assignment. So I have an example for you. Okay, let us start from this. This is the original data. all the samples are here, the green ones and basically all are green ones. And I initialize my mu. These are my two mu values. So this is deliberately taken to be very bad points to show the convergence, that how efficiently or how nicely this algorithm converges. So these are the two centers, the two mu's in this case. So now I have to find the cluster assignment. I have to find R and K. How do I do it? So, okay, this is this part. So given the mu K, I have to find R and K. Now, I go to each sample, I ask it, if you look at this original loss function, if I go to each sample and I ask it whether this should be xn, not xk, sorry. Okay, so I ask whether xn is closer to mu1 or mu2, right? If it is closer to mu2, then this will be smaller for mu2, so then I will say, okay, Rn2 is 1. Basically, this n belongs to the second cluster, not the first one, right? So in this way, I will find all my R and K. So I go back to this example. So here you see, let's say this sample. This sample is closest to this point, not this point. No, sorry, this center, not this center. So that is why I will assign it to this cluster. So all the red points are those which are assigned to this cluster center. And all the blue ones are those which are assigned to this cluster center. In this way, I have estimated my R here, right? The next thing is, okay, given the R, I have to estimate my mu. So that is a simple, optimization. What is it called? Maximum likelihood estimation. So basically, you take all your samples and try to maximize this loss function with respect to this unknown parameter, which is mu in this case. So I am differentiating L with respect to mu, keeping R and K as given. So let us say dou L upon dou mu K dash. So K dash is the one which I am going to estimate now. And this comes out to be this thing, which I simply solve it and I get this function. So it is basically if you analyze it closely, R and K is either 0 or 1. So it is the mean of all the points which are assigned to the K dash cluster, right? It is just the average of all those points which are assigned to the K dash cluster. Okay, so let us see in our example here. So these red points are there. What is the average? It will lie somewhere here, right? If I take the average, that is where now the red point has moved. This red point moved from here to here, the red cluster center. Okay, in the similar way, the blue ones are here, all the samples are here. Now I take their average will lie somewhere here. So that's where now I updated my blue cluster center to come to this point. Okay, now I estimated my mu's. Given these mu's, now again I estimate my cluster assignments. Again, if you do look at each point, now see this point. This point was earlier in the red class or the red cluster, but now it is closer to the blue cluster because the blue cluster center has moved here and the red cluster center has moved away. So this point will naturally be reassigned to the blue cluster. That is what happens, and you get this assignment now. You see, even just in 2 iterations, it has converged very nicely. Okay, so now you again update your cluster centers and they are again updated. Again do reassignment, again cluster center update, and again reassignment, again cluster center update. And you see after the second iteration, it is not changing much, right? So looking at the loss function or looking at the movement in cluster centers, whatever criterion you want to take that as your criterion and put a stopping criterion. Whenever this falls below a threshold, stop there. So that is the k-means clustering. So what are the parameters here? Mu and R, right? And what are the hyperparameters here which are playing an important role? Number of clusters, which means K, capital K. In this case it is 2. It is an important hyperparameter which you do not know a priori, which you may not know a priori. You may not know how many clusters are there in your data. So you have to do some inspection to see if the clusters are good or not. Okay, many times this algorithm may be stuck in some place. Can you think of such situation? Can you think of a situation where this algorithm will be giving very bad clusters? I'll give you an example. I'll give you a hint. The hint is that it is doing hard clustering. We have seen this problems with hard clustering or problems with hard assignment in the beginning of the course. Uh-huh. Didn't get it.
There are two clusters of the same kind, and this other cluster is in between.
Huh.
So these two are of the same kind, but one line cannot be.
Okay, you're saying that let us say we have 3 clusters but we have only 2 hyperparameter. Hyperparameter value is 2, then it cannot do it. That is clear because then we take 3, then it will be able to do it. If I take 3 centroids, then they will be able to map all those 3 sample clusters. Yes, good example. So, what's your name? Soumyadeep is suggesting, let us say we have this distribution where the data is concentric, let's say concentric circles. So this is one data center, sorry, this is one data, this is another data. So k-means clustering cannot handle this kind of data, this kind of clusters, right? So what is generally done in this case, you take k to be larger than 2, let us say I will make this as one cluster, this as another cluster, this as another cluster, this is another cluster, right? So if you take more number of centroids, then you will be able to do a better job.
So for this problem, we can also do a transformation.
Yes, transformation also is possible. I can transform in a way that they become separable. Okay, means I project it to a higher dimensional space where they become separable. If points are far apart, then good. Yeah. So very good insight that if we have outliers which are very far, let us say I have one cluster here, and one outlier here, right? This will spoil my whole clustering. Now the cluster, let's say I'm finding 2 clusters. So ideally it should have been this cluster, and this outlier should have been ignored. But in this case it will be this cluster and this singleton. Singleton means a cluster with a single data point. So that is the problem which we may face here, right? Okay. Okay. So coming back to our main stuff, how would you model this data? So this data is a multimodal data. So I'm just doing a small recap from where we started. We have multimodal data. We saw k-means clustering, which has its own merits and demerits. The merit is that it is very fast. It is very efficient. Even for higher dimensional space, it is very fast, very efficient. But demerits are, let us say, it gets stuck in with the local, with the outliers. It is not very robust with outliers, and it is doing hard clustering, which is not a very nice thing.
The previous example, so there was the outlier. Shouldn't the distortion measure prevent you from clustering this?
Yeah, you have to modify a distortion measure in certain way, right? You can modify your distortion measure in some way. How will you do that? You, like how we did it in the last case. You put a cut clip, right? If the distance is too large, clip it or saturate it to some value so that it does not pull very hard. That you can do. Okay. Now we'll come back to our original topic, latent variable models. So where we started from. So basically, we have our distribution P of X. X is the samples, the data which I'm observing. And I want to estimate P of X. If it is multimodal, then I do not have any standard distribution to do it. So what I will do is I will take latent variables called Z. So Z is the cluster variable. So let us say the Z belongs to the first cluster, then this is the distribution. If Z belongs to this cluster, then this is the distribution. And then you marginalize over Z. So this is basically P x comma Z marginalized over Z. This is the thing, right? And P x comma Z could be anything. It could be Gaussian, it could be exponential, it could be Bernoulli distribution, any distribution basically could be Px given Z. And Z is a discrete random variable. It can take discrete values like 1, 2, 3, 4 up to K. So this is the idea of latent variable models. They simplify our job by clustering the data and modeling each cluster separately. Okay. So now we'll discuss an important latent variable model called the Gaussian mixture model, in which there are clusters and each cluster is modeled with a Gaussian PDF or Gaussian distribution. So I have got my data X, the samples, and I have Z as my latent variable, which is the cluster index. So Z could be 1, 2 or K. It is a discrete random variable. So this is one representation of Px. Equivalently, I can say, now I define my Zk as the kth element of a one-hot vector, right? And you know one hot vector will have 1 only in one position and everywhere else it will be 0. So wherever it is 0, it means it does not belong to that cluster. Wherever it is 1, it means that cluster, that data point belongs to that cluster. So Z is basically so my Z, or you can call it as Zk for a particular n. This is for a given sample, right? For a given sample, Zk will be, it will be a one hot vector, so it will be 0 in most of the in all the places except one place where it is 1. So in this case, it's the third cluster, right? So this indicates third cluster. So this is the idea of Zk. Oh, sorry, this is the Z vector. I'm sorry. This is the Z vector. And in this case, Z3 is equal to 1 and Zi equal to 0 for all I not equal to 3. Right? Equivalently, I can also use Zk is equal to delta K3. Another way to write, just the point is clear that I want to say, okay, this is my cluster. Basically, Z is the cluster assignment variable, right? Okay. So don't get confused if you see different notations in the book, but I've tried to follow the book's notation. This is from the PRML 9th chapter. So I've tried to follow the book's notation with slight modification, but mostly it is from the book. So this is how we represent. Now P of Zk equal to 1. What is the probability that this cluster is chosen? So that we can assign, we can call this as a variable pi k. Pi k is probability of Zk equal to 1, right? And P of x given Zk, probability of the data samples given the cluster. So we are modeling it with a Gaussian, that it is a Gaussian distribution. So this is the cluster centroid, cluster variance or covariance. I think we have discussed the multidimensional, multivariate Gaussian distribution, right? So here mu is a mean vector and sigma k is the covariance matrix. If you have not seen, no problem. It is just an extension of the univariate case. You can read it in the book. It is very simple. I think we discussed it in the last class. Okay. Anyways, we'll be doing it again today. So now come back to our original basics. So we are given the samples Sn and we want to estimate the parameters of the model which we have chosen to be Gaussian mixture model. So I've given the samples, I want to estimate the parameters of my Gaussian mixture model. K is the hyperparameter. How many Gaussians do I want? How many clusters do I want? So K is a hyperparameter which we have to tune. Okay. Now lots of maths today, but it is all very easy. If you just stick to the basics, it is very easy. Okay, so the idea is we use maximum likelihood estimation, right? All of you already know this. So just focus on the pointer and things above the pointer, then you won't be confused. So we start from here. We define the likelihood function, which is or log likelihood function, which is probability of this sample given the parameters and summation over all the samples, right? This is my probability, this is my log likelihood, right? Now I will expand this P of sample given theta. In case of Gaussian mixture model, it is this, right? That probability, it comes from the kth cluster into probability of the sample given the cluster summed over all the clusters, right? This is my P of sample given theta. Okay, now what is this normal distribution? It is simply 1 upon 2 pi. This is then what is it called? Normalization term, and then exponential of half of the S minus mu transpose sigma inverse S minus mu. This is for the multivariate Gaussian distribution, right? This is simple PDF. Now what do I do next? I differentiate this log likelihood with respect to the parameter which I want to estimate, right? All of you know this basic theory. So I differentiate with respect to mu k dash to find the optimal value of mu k dash. Okay, so this function looks complicated, but actually it is very simple. So differentiated with respect to mu k dash, you get log of something is 1 upon that thing into the derivative of this thing. So since this is a function of k dash, so all other k's will be 0, only k dash will come into picture. So pi k dash into this, oh there is a mistake, it should have been k dash here. This is a k dash, this is a k dash, and this is a k dash, and this is also k dash. Okay, so basically, how do I obtain this? So this is some constant into exponential. What is the derivative of this thing with respect to mu k? The same constant. The exponential times the derivative of the exponential term is the term in the exponent with respect to the mu k dash, right? So now here I have to write the derivative of this thing in the superscript. So which is equal to there should be a half term also. Oh, but there is a square, so the half will go away. Okay, fine. Now the derivative of this thing with respect to mu k dash is simply sigma inverse times this times the derivative of this thing, which is minus 1. So this is just a vector calculus or matrix calculus, which we have already seen before. You know if you don't remember this, you know where to look it up. So that is the Wikipedia page of matrix calculus, right? So all these derivatives are given. If you're interested in derivation, then you can also do that, but just the formulas will be sufficient, and they are very intuitive. Okay, now I got this. I put it equal to 0. Now this thing will be occurring in so many other places as well. So I will denote it with a symbol called gamma nk. This gamma nk basically, this thing is a function of n and k. Actually, it is k dash. Again, gamma nk dash. So this gamma nk dash. So let us see what is this term. This term is the probability of S given this cluster into the probability of this cluster divided by the normalization term. So basically this is a soft assignment. If you compare it with the softmax function, right? If you compare it with the softmax function, so this is probability that my S belongs to this cluster divided by the probability that S belongs to any other cluster, right? It is summed over all the clusters, right? So this is a kind of soft assignment term. right? So my gamma nk is a soft assignment. Earlier we saw the hard assignment in k-means clustering, but this is a soft assignment thing. Okay, so this is something like probability of zk equal to 1 for this sample n. So this is like probability that Sn belongs to the kth cluster, soft assignment. K means did the hard assignment. Okay. Now I have to just solve this equation for mu k dash, which is very simple. I know, okay, sigma k is common. It is not a function of n, so we can throw it away. Only this gamma thing is a function of n, so I cannot take it outside this in summation term. So outside this summation. So what remains inside the summation is only this gamma term, s and mu, right? And when I split the terms, it becomes this thing. So simply mu k, or you can call it mu k dash. So the dash are everywhere. So my mu k dash is simply summation over all n gamma nk dash Sn upon nk dash. Now compare it with the k-means clustering case. What was the mu? Mu was the average of all the points which belong to this cluster, right? In this case, since we have soft assignment, so these weights get multiplied. So the weight of this sample, which means the probability that this sample belongs to this cluster, divided by all the sum over all these weights. Nk is sum over all the weights, right? So this is the thing. This is the maximum likelihood estimate for mu k. Similarly, I can do for sigma k. So the same thing will follow log likelihood, and I differentiate with respect to sigma k dash. I get this derivative. This derivative is little involved. This derivation is not there in the book, so I did it just today on my own. So there might be some mistakes, but it's very unlikely that there is a mistake here. So basically there are two terms, one in the normalization constant, the other is in the exponential. If you differentiate them one by one, this is what you get. You have to use some formulas from matrix calculus, because we are taking the derivative with respect to a matrix now. We have not seen this in the past. We have only taken derivatives with respect to vectors. This is also something similar. The formulas are given in the Wikipedia page. You can refer to them. So basically the derivation is given here, it's complete, and this is what you obtain finally. So the variance is, or the covariance matrix is given by S minus mu k. So if you compare it with your Gaussian, I'll just write it down. If you compare it with your Gaussian case, with like a single Gaussian, let's say univariate Gaussian. So what was your estimate for sigma square? Sigma square ml was equal to summation of x minus mu whole square. Sorry, this is n. So summation over all n divided by capital N, right? So this term is something similar. So this is s minus mu k into s minus mu k transpose. So that it is essentially x minus mu whole square, and then the soft weights divided by sum over all the weights, right? Something very similar. So this is how you estimate your covariance matrix for each cluster. Next is you have got the cluster probabilities pi k, probability that zk is equal to 1, right? This is also a hyperparameter which you want to estimate. So, but you cannot simply differentiate the log likelihood here, because my pi k are constrained to be PDF, means their summation should be 1, right? So if you simply differentiate it, you won't get anything, because it will say, okay, keep increasing pi k, because I want pi k to be large. But that won't help, because pi k has a limit. Pi k cannot go beyond 1. I mean that pi k is greater than 1, and the sum of all pi k's should be 1, right? That is why you will impose this Lagrange multiplier, and then you differentiate this whole term. It becomes something like this. This part is, you already know this part, and plus the lambda term. So because it's lambda pi k, so ik dash, so it's lambda term added. Now in Lagrange multiplier, we also optimize the value of lambda, right? Why not? So lambda can also be optimized. So in this term, there is no way I can find lambda. But if I use a simple trick, and the trick is that you multiply with pi k dash, the whole thing, and sum over k dash. So what do you get? If I multiply this with pi k dash and sum over k dash, this becomes 1 because I know my pi k dash summation over k dash should lead to 1, right? And then this term, if you take pi k dash and sum over all the k's, the numerator and denominator will simply cancel and you will get sum only over 1, right? So your lambda comes out to be minus capital N. Substitute it back in this equation, equation number 1, and you also substitute that your pi times this thing is gamma nk dash, right? And so this term is basically gamma nk dash upon pi k dash. So from here you can easily estimate the value of pi k dash, right? Because the gamma nk dash you use your previous estimate. Because we are not estimating all the parameters at once, we are estimating them step by step. Means you estimate one parameter while keeping others constant, and then iteratively you estimate all the parameters. Okay, so this is what, now summarizing the whole algorithm, maximum likelihood estimation for Gaussian mixture models. So okay, same thing which we discussed just now. None of the estimates is independent of each other, right? Earlier we saw for Gaussian, the mu was independent of sigma, right? The univariate Gaussian. I could simply say my mu is the average of all the points, and then sigma depends on mu, but since I have already estimated the value of mu, I used the estimate of mu there and I was done. But in this case, you do not have any variable which is, or any parameter which is independent of other parameters, or the estimate of which is independent of other parameters. But that is why you have to do it iteratively. So we follow the iterative approach as in k-means. So what is the approach? First of all, initialize all the parameters. That's what we did in k-means also, if you remember. We initialized our centers, right? And then we optimized our mu. Same thing, initialize all the parameters, the centers, and then assign. Assign means calculate your which point belongs to which cluster, which means gamma k. Gamma k is your soft assignment of the sample to the kth cluster, right? So gamma k is 1 if your point belongs to that cluster. It is 0 if it does not belong to that, and there are intermediate values which show partial membership. So assign, calculate all the gamma k dash, and then given those clusters, those assignments, again update your theta. That is the next step, right? And then if you have converged, then you can stop, but if you have not converged, then again reassign, update your each cluster, again assign, again update your each cluster. In this way, you do it iteratively. So very similar to k-means algorithm, just the formulas and the assignments have changed. Okay, now coming to a very general form of this algorithm, which we just now discussed. So basically, GMMs are not the only latent variable models. We can have so many latent variable models. And for all the latent variable models, one approach which is very useful is expectation maximization algorithm. It is very efficient and it is very fast. It is very it's very much used. Okay, if I give you any loss function and I ask you to optimize it for a particular parameter, what will you do? The most general thing you would think of. I give you a loss function which has parameters which you want to estimate. Now you want to maximize the loss function with respect to those parameters. What is the thing that you will do? Differentiate it, put it equal to 0, and solve for analytical solution. But if analytical solution is not possible, then what do you do? No, but iterative approach is there when you have okay, let me write down. The simplest approach is that, okay, given L, uh, find optimal value of theta, right? So what are the different approaches? So one approach is you say dou L by dou theta is equal to 0 and solve for theta. Many times, if thetas are interdependent or theta MLs are interdependent, then you use iterative update. Basically, you do them in tandem. It's called in tandem. In tandem means you assume the initial values, then estimate one parameter, fix it, estimate the other parameter, fix it, estimate the earlier one, fix it, again estimate the other one, fix it. In this way, you do it in tandem, like one after the other. Okay, but this is possible only when this is possible. Possible if dou L upon dou theta equal to 0 is solvable for theta. What if it is not solvable for theta? It is very dirty form, like some log term, some exponential term, some multiplication, some division. It is, you cannot derive an analytical solution for dou L upon dou theta equal to 0. What will you do then? What will you do then? This is called conditioning. I'll tell you how. If I would have asked you this question maybe a week ago before teaching this, you would have immediately given the answer. You would have immediately given the answer. Gradient descent. But now, since you have been reading all these stuff, you have been conditioned and you have forgotten the basics. So, okay, so we will use gradient descent, right? The most obvious solution which works everywhere, use gradient descent. If dou L upon dou theta not solvable, that's what we did with deep learning. Use, just a minute, gradient descent. Yeah, that's why I wrote in tandem. I didn't want to confuse you. Right? Which means that you exactly solve for one theta to find its estimate, keeping other thetas fixed. But if dou L upon dou theta is not solvable at all, then you use gradient descent. Okay, then there is an intermediate approach where you cannot solve perfectly, means very easily, and you do not want to use gradient descent because gradient descent is inefficient. All of you know that is inefficient, and if the loss function has some structure, we can do better. So that is why we go for an intermediate approach, which works very well for latent variable models. It's called the expectation maximization algorithm, or EM algorithm in short. So what is the EM algorithm? So this is what it does. You have probability of x given theta, means x is the samples. I have denoted it with S to say that these are the samples which you have actually observed. Probability of samples given theta. This is what you want to estimate. You want to maximize with respect to theta to find your ML estimate, right? So this part is clear. This is what I want to optimize with respect to theta. So, but if I am using latent variable models, it becomes something of this form. Probability of S comma Z given theta marginalized over Z. And Z are my latent variables, right? Z's are the latent variables. Now, there is a problem. What is the problem? The problem is this summation inside a log. If you have multiplication inside the log, as you have seen before, if there is multiplication inside the log, it solves very nicely. Okay, so I'll go further. So you split this in terms of the conditional probability of z given theta into probability of, okay, it's not x, it should be s, into probability of s given z comma theta, right? That's what we did. Probability of the clusters into probability of sample given the cluster, right? But this thing is not easily solvable. Only in case of GMMs it was solvable, but in general it is not, right? So let us see the problem here. I have taken, the green ones are the examples with GMM. So Pz given theta is simply pi k, and Ps given z given theta is the probability of sample given the cluster or the cluster parameters mu and sigma. Now you see the log is operating on a summation, so you cannot use that property that log of a into b is log of a plus log of b. You cannot separate the terms, and if somehow this term means mostly this term will be not analytically solvable. So that is the problem. So this term, the normalization term, the normal distribution term is an exponential. If this summation would not have been there, I could have operated this log on pi, so it would have become log of pi plus log of this exponential term, which is very simply, you can remove the exponent, it becomes a quadratic term. Very nice function it becomes. It would have been just like you saw the case of least square error estimate, least square estimate for regression, it would have become something similar. But because of this summation term, this is not possible. How to get rid of the sum inside the log? That is the basic philosophy of EM algorithm, to get rid of this summation inside the log. So very simple observation. The observation is that probability of s comma z given theta, probability of s comma z. If somebody tells me these are your samples and these are the clusters, then I can directly get my P of s given z, and I do not have to marginalize over z, and this term is exponential, so I can very easily optimize my thetas. Analytically I can solve the thing very easily because there are no summations inside the log term. But I do not know z, so what do? Assume a value of z, assume some value of cluster assignments, the z, and later average over all z. Means, okay, I took one assignment, another assignment, like in the whatever number of assignments are possible. Each sample can go to, let's say there are k clusters, then each sample can go to k clusters only. So similarly for each sample, let's say there are capital N samples, so n to the power k, that many possibilities are there, right? So you average over all these possibilities. Of course, all these possibilities, not all of them are equally likely. Some are very unlikely, some are more likely. Like if you average over all of these, then it is a reasonable loss function, right? So what we are trying to do here is we are trying to create a new loss function. That is the Q. It's a new loss function. So what it does, assume, take the joint distribution. Do not marginalize over z here, but you average this loss function over all possible assignments, which is this. Probability of z given s comma theta summed over all z. Right? This is so the whole thing will be average. Okay, actually I think you might get little confused for, so this summation is over everything, not just over. Summation is over everything. Right? So you take the joint distribution, do not marginalize, but you take your log on this joint distribution and then take average of this log over all the possible assignments. So you get something like this. Q is expected value of z. If you remember, don't be frightened with this e term. It is simply whenever you see summation over summation over a random variable into a function of the random variable into probability of that random variable you can simply write the expected value of that function, right? Okay, now another problem is waiting us. That problem is there is a theta term here as well. So when you take the derivative, this theta term will also appear. It will make your analytical calculations more difficult, right? How do you avoid even that? You can even avoid that by assuming an old theta. So you're updating your theta, it's an iterative algorithm. So assume that this theta is your old theta, not the new theta. So which means it is a constant thing, right? And whatever is the variable is only theta. So basically, the goal is you want to do argmax over theta of q, which is a function of theta, but you say this is also a function of theta old, and this thing won't vary when you vary theta, right? Because this is fixed with respect to the new theta. That's what you have done here. So you have taken this theta old here so that it does not interfere with your calculations, your analytical solution. This is the EM algorithm. I have done it for the Gaussian case. You can go over it. It is very simple. Just the same thing. I just substituted. I found the Q function for the Gaussian case. So you see the Q function is simply PZ into log of the joint distribution. Joint distribution is simply, if you know the cluster, it is simply P of Z into P of X given Z, right? You already know what is the Z, what is the cluster. And then outside the log, you are averaging over all the clusters, right? Gamma nk is the assignment operation, soft assignment operation. Okay, and the same algorithm will follow. Initialize theta old, assign the clusters. This is basically you compute your gamma nk. This is the E step, and then update your parameters. Given this assignment, you update your mu, sigma, and pi, and then again for maximizing your Q function, and then again do it iteratively until convergence. Okay, so that is the EM algorithm. If you want to read, okay, so this everything is there in PRML section, chapter number 9. It very nicely explains. If you want to do more further analysis of EM algorithm, which is not mandatory, but if you want to explore it, it is a good exercise. You can read the section 9.4. It is not mandatory. It is up to your interest. If you are interested, you can read it. It will tell why the EM algorithm converges to a good solution. The convergence proof, basically using some divergence and another interpretation of this whole thing. Okay, but EM algorithm is a very useful algorithm for latent variables. So you have got different kinds of latent variable models, and for all of them, EM algorithm is the first choice because it is very efficient and very fast. Thank you. So.